Hello again, and welcome to what I guess is the penultimate video in our series. We are going to do a bit more with graphing parametric equations. I have a list here of some tips to kind of help us as we go through this. And let's just see what we have to say about this. Because really, there's not much else to them as to what they are. They're a pair of functions, right? X coordinates are given by one function, y coordinates are given by another, and you put some third variable t through each of them to get your outputs. And so you get a sequence of ordered pairs. You then plot those ordered pairs, connect your dots, and you have a graph. And so with that in mind, here's some tips to kind of keep us organized as we're working through them. The first thing we might want to consider is just making a table of values. Except now, instead of what we used to have with inputs and outputs, now we have input, output, output. So t goes in, t is our independent variable, and x depends on t, so we get some x value out, and y also depends on t, so for that same value of t, we get some y value out, and that makes us then have a list of ordered pairs. If we write t in order, then we are good to go, because our ordered pairs we can now plot in order. And once you've done so, just connect your dots using arrows to go in the way you're increasing, or in the way you're moving, and that will be your graph. You just keep going until you've got a pretty good handle on what should be your function as a whole, or what should be your graph as a whole. Just kind of extrapolate from there. If it helps, which it sometimes does and sometimes really doesn't, you can try eliminating the parameter, which means turn your pair of equations into simply a rectangular equation, or one single rectangular function. Because we're good about graphing functions, especially if we already have had the algebra side of pre-calculus well in hand, or have had that, or we have a good ready recollection of that. Because if we can turn our plane curve into something we can graph easily, we can then simply superimpose our knowledge of the behavior of the parametric equations to be whatever direction we should be moving in. So let's just do a few. Let's just go for it. I have an example here, and there's a couple of things we can say about this. Obviously have a pair of equations here. X as a function in t is given by 2t plus 1. Y a function in t is given by t plus a half quantity squared. And as always, we're going to want to make a table of values to see what we're looking at. And it might be helpful to eliminate the parameter. I kind of have a setup for us here as to how to do that. But I very deliberately cut off what that equation is going to look like. Because let's go ahead and just plot this thing by plotting points in order and seeing what we have. So again, x of t is 2t plus 1. So negative t goes to 3, negative 1 goes to 1, and so on and so on. And then y of t is we add a half and square that, and so that will give us these values here. So what we do is what we always do, and we plot some of these points. I guess more to the point, we plot all of them in order. So first guy is negative 3 comma 2.25. So right there. Next point is negative 1, 0.25. And then again at 1 comma 0.25. And then we are at positive 3, and then positive 5. First there, and then down to here. So those are our points. In order, they look to be doing something like that. And also, they seem to be going in that direction. And that's what we get based on the points we plotted. If you're not confident with that, right, for instance, if we really need to know where this vertex is, such as it is, we can plot still more points, or we could take the time to do an elimination of the parameter. So let's see here. If x over 2 is this thing right here, I'm looking at then y is going to be x over 2 quantity squared. So I guess that means my vertex that I plotted here was not quite correct. It should actually be more like that. And it's a good time. So I hope you're seeing what we're doing here. We're just plotting some points, connecting our dots, and if we need the behavior, we can plot more points. Maybe we can eliminate the parameter, turn it into a nice plane curve, and see what exactly it looks like, and just use the parametric effect to figure out what direction we're moving in. I have another example for us here. I want us to look at now the parametric equations given by sine squared t and cosine squared t. And so we'll make a table of values. We'll worry about this comment here in a second. Let's just go ahead and make a set of comments. So sine squared, we can run all the way through, right? Sine of pi over 6 is a half, squares to 1/4. Sine of pi over 4 is root 2 over 2, which squares to 1/2. And then root 3 over 2 squares to 3/4. And we just kind of work our way around. Note that we never go negative because we keep squaring things. But note also that I can add my two coordinates and I always get 1. So let's kind of see what we have here. Trash this right quick. So we're looking at 0, 1. We're looking at 1/4, 3/4. We're looking at a half, a half. We're looking at 3/4, 1/4, and then 1, 0. And what happens is we go down, and then looks like we go back up the same way we came. And then we go back down again, and then we go back up again. And it repeats forever. So one way to draw that would be to have arrows in one way. This is not working well. Would be to have arrows in one direction and also arrows in another. Wow, that is not looking right. So I guess arrows in one direction and also arrows in another. Because you're doing everything. You're going back and forth over and over again forever. And it's just that one tiny little chunk, right? Just that one tiny little chunk. And I say that because that's very important, because I want you to compare this to what you would have gotten from eliminating the parameter. Right? So I got sine squared t plus cosine squared t. Well, that's always 1. So since this is an identity, I can substitute back x plus y is equal to 1. So if you eliminated the parameter and graphed the overall plane curve, you get that right there. But our parametric equation is not this whole thing, but rather it's saying, okay, I want just this one tiny little sliver, and I want to go back and forth on it. That's something that this equation couldn't even begin to say. Unless, I guess, you very specifically restricted the domain on it, in which case, okay. But that's what we're doing. That's how we're doing this. And really, that's all there is to say on the matter. Just do what you can, see where it takes you, see what you're looking at. It's really just a fun way, for now, right? It's just a fun way to add a little bit of spice, a little bit of flavor, a little bit of information to equations and systems that we could not previously have been able to do. And that's just exciting. It's just fun to do something, to move in a direction, and I mean this in a very real sense, right? To move in a direction we haven't previously moved. And we can go in one direction, we go in the other, and now we can also apparently oscillate. It really is just a wonderful world to live in. And don't be too stressed out about the specifics of this business that we're in now with parametrics. This is a survey. What we're doing here with these systems is a survey on them. I am showing you what can be done with them and what they look like and how to make some simple graphs by plotting points. And if you can do that, you're in good shape for this class. And actually for a good bit to come. Polar and parametric is so heavily rooted in very specific applications that it does take a while to resurface. So as long as you've got this level of familiarity with it, you're going to be in good shape. So that's it for now. I've got one last video where we do just a couple more examples right quick, and then we will be all set. So have a good one. I will see you then.